All right, calculus, here we are for your Wednesday, the 27th of October notes. We are in section 2.8, day 3, and truthfully, this might be the last day for 2.8. We are almost there. I'm going to take a look at some more examples on Thursday, or I might start giving you some help with that new and improved quiz review. All right, for Thursday, we shall see. Going to be a surprise. And then like the same thing on Friday. Thursday and Friday will be great days as well to get that homework set done. Homework set 3, homework set 4. All right, early and often on the homework first, folks. Practice it early and often. So, page 159. Let's look at that in the book that we technically use. Look at the bottom here of page 159. All right, so let's talk about first and second derivatives. In general, we can interpret a second derivative as a rate of change, The most familiar example of this is acceleration, which we define as follows. If s, which equals s of t, is the position function, see, you can mostly see all that, of an object that moves in a straight line, we know that its first derivative represents the velocity. V of t, velocity, is the derivative of the position function. The instantaneous rate of change, oh, we've heard that before, with respect to time, the instantaneous rate of change of velocity with respect to time is called the acceleration of the object. Thus, the acceleration function is the derivative of the velocity function and is therefore the second derivative of the position function. Now, in chapter 3, when we learn about the very easy derivative rules, we'll start working with acceleration. But velocity is fair game right now. So here you go. Or in Leibniz notation, all right, acceleration is the derivative of velocity. Again, it's with what? Respect to time, dt, that's just telling you that t is the variable that you're differentiating, or it is the second derivative of the position function. Acceleration is the change in velocity you feel when speeding up or slowing down in a car. Okay, then you have a third derivative, which we won't do a ton. But we can. You can find like any derivative you want. You can find the 10th derivative if you want. All right, so let's talk about that. So know this. That s, which is s of t, is the position function. V of t is the derivative, s prime of t, or ds dt. T is the independent variable. You're going to be taking the derivative of t. V of t is the velocity function. A of t is the derivative of velocity, or the second derivative of speed. So it's the derivative of velocity, or the second derivative of speed. A of t is the acceleration function. Also know this. So folks, this is essentially, again, you have the difference quotient, and you have the definition of a derivative, the limit definition. V of t is that. Only this time, we're going to be plugging a number in for t. Note that s equals s of t. Sometimes they use h for h of t if you want to know the height of something. All right, so we got a few of these because you're gonna spot them. So suppose that the height of an object t seconds after being launched from an initial height of 20 feet is given by that equation. Find the instantaneous velocity at time t equals 2. So first off, I need to figure out what's the height of the objects at time t equals 2. So f of t again is a number here. T is a number. We're not finding just a general derivative. We want to know the instantaneous velocity. So you got to plug 2 in for t, which I have done over here. Plug 2 in for t and you get 136. All right, and then again, it's 2 plus h. So h is you're gonna have an h in here, and t is gonna be a number. So it's gonna be f of, in this case, 2 We got 10% on the battery, so we're going to make it 2 plus h. Plug 2 in for x. And h in for x plus. Plug 2 and h in for x there and there. This is the whole f of 2 plus h minus, or in this case, s of 2. Again, s and s or f and f, it does not matter. All right, so I'm doing a little algebra there. Okay, there we go. 180 minus 116, that is 64. That's good. It cancels with negative 64. Again, you know the constants must cancel. You can be only left with something with h. You can pause this when you need to. We have the limit as h goes to 0 of negative 16h plus 26. That means if h is 0, it's 26 what? Feet per second. So it's still going up. Velocity is positive. It's still going up. So in college algebra, we learned about how long does it take to reach its maximum height. What is the maximum height? We can do that so much quicker now with derivatives next chapter. Okay, cool. So we're going to try another. Again, we have to use the limit definition. And I made a boo-boo on too. I was thinking about something else. I was doing that. Oh, a pumpkin. It's catapulted into the air, and its height at time t is modeled by that equation. Again, heights in position and s, they're the same thing. It does not matter. Okay? So we're going to use this definition. Again, that maybe should say h. Again, the function with the independent variable t. All right, so find the instantaneous velocity of the, what? Of the rock. What in the world is that? Of the pumpkin. At t equals 2 seconds. Again, so I made a boo-boo. That is h plus 2, h plus 2, and I rearranged it as well. I put the negative 16t plus 130 t plus 4. This is the second time you've seen negative 32 t. So this is if you take the second derivative, you get negative 32 feet per second squared. Or actually, if you take two derivatives. So that's acceleration in terms of feet. You know of the negative 9.8 meters per second squared. So this is in terms of feet. 130 is the initial velocity, and 4 is the initial height. So we talked about that in college algebra as well. Okay, so this is the whole f, or in this case, h, of 2 plus, again, another h. All right, so plug 2 plus h in for x. Minus, I made a mistake. You should plug 2 in. You should plug 2 in for t, negative 64 plus 260 plus 4. That's a negative 200. So we're going to go down to here. Let's do the algebra. That plus that is 264. Negative 64 plus 264 is 200. Minus 200, they cancel. What's going to happen with the h's? You're going to have 66h, negative 16h squared. Again, we don't need, that doesn't need to be there, that doesn't need to be there. It should be 200, 200, 200. Okay? Divide by h. The limit as h goes to, forgot that, 0. It's going to be 66 feet per second. 66 feet per second. All right, so it's still going up. It's still going up. Find the instantaneous velocity of the same, gosh, why did I write rock? Hopefully I didn't have this typo a few years ago. This was the official notes we used when SLU was in the building. At time t equals 5 seconds. All right, so I'm plugging a 5 plus h in to that same equation where I see t. And I plugged 5 in for t. It's a negative 16t squared plus 130 times 5 minus, and then plus 4, and you get 254. All right, I did the algebra, squared everything, and multiplied everything by negative 16. And I combine like terms. This minus this, plus this is 400. 140h, the 400s cancel, yay. This and this gives you a negative 30h. And I plug 0 in for h, so it's coming down, negative 30 feet per second, it's coming down. Awesome. It's the difference quotient. It's the definition of a derivative. This time we're plugging another number in, all right? Plugging something in. Instead of having an x, we're plugging a number in for x. So it's very similar to the limit definition of a derivative. That's why it should be relatively easy to have all of three things memorized. All right, we'll talk more about, we just did 3 with velocity, so we should be good. So if you see one of those on your homework set, that's how you do it. Given f of x is equal to 4x squared minus 5x, find the general derivative, f prime of x, as a new function using the limit definition. So you have to have that memorized. Pretty similar to what we just saw. Okay. So I'm plugging x plus h in for x there and there. It is f of x plus h minus f of x, parentheses around both, so you actually add 5x. All right. We should know how to FOIL that pretty quickly now. We got that. I have canceled the negative 5x with the positive 5x. And look at that, the negative 4x's squareds are going to cancel, leaving me with this. The limit is as h goes to 0. I'm going to divide everything by h. And now this time I'm going to let h be 0. And it's equal to that. So you did a whole bunch of this with the difference quotient in chapter 1. Now we're just simply letting h be 0. We're making sure to write limit as h goes to 0 the whole way through. And there's the general derivative. Why is that important? If I want to know the instantaneous rate of change of this function at x equals negative 3, at x equals 10, at x equals negative 100, I just plug that in for x. All right, if f of x is equal to 24 over root x, find f prime of 9. So first I need to find f prime of x. Again, in a few weeks this will be made a little quicker, but this is good to practice this way. So it needs to be f of x plus h, plug x plus h in for x, minus f of x all over h. Holy cow, this one takes a while. Hopefully you have a lot of room, or else you're going to have to go to the next page like I did. So I wanted to combine the two fractions in that true numerator. So I have to give this first fraction. Now I can't just simply put a plus h and extend it. All right, I got to give that a root x plus h, root x plus h. All right, and then that's my numerator in the numerator, and that's my denominator. Okay. And then, here's what I did, okay? So this is the true numerator, and this is the denominator. Guys, if you're dividing, if you have a fraction you're divided by something, whatever that, this denominator is, you're just going to multiply. All right, this denominator here is going to get bigger by a factor of h, so I put the h with that right there. Because you're going to multiply by 1 over h, the h is going to stay down here, okay? So that should be easy to see. If I'm this divided by this denominator is going to get bigger by a factor of h, so h goes right there. All right, so kind of have an issue here. Now what I did next is I factor out the 24. Probably could have done that earlier. I factored out the 24, leaving me with root x minus root x plus h. You know at conjugate time. So I'm going to multiply the top and the bottom by the conjugate of this, root x plus h. And that's going to give me just a mess down below. This times the conjugate. But up top, I'm going to have x minus the quantity x plus h. The x's will cancel, leaving you with a negative h above. Now, here's what I also did. Okay, so this h times root x, that's staying in there, but I have a root multiplied by itself. That's why I have x plus h. Then I have plus. I multiply these two together. Put the root x on the outside times root x plus h, just like I have right here. Okay, that's how I simplify. Now what's going to happen? The h's are going to cancel, which is good for us. All right, the h's have canceled. Now I can officially let h be 0. So here is what happens. So first off, when you let h be 0, you're going to distribute root x times x. That's right there. And then what happens here? Root x times root x is simply x. And x is going to be multiplied by another root x, because h is going to be 0. So that's why there's 2 of these in the denominator. Wow, I was right. Man, that's a lot of work. Holy cow, what's f prime of 9? I'm going to plug 9 in for x. And you finally get the derivative of -4/9. The instantaneous rate of change of -4/9. Wow, 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 wow. That was a good amount of work. Why don't we finish it up with just one more? Great opportunity to finish all your homework after this one. If f of x is equal to the square root of 4x plus 5, find f prime of x. When we talk about the chain rule, that won't be right away. When we're talking about easy derivatives, that'll be pretty quick. You know how to do this one really quick. All right, a little quicker than this. So I'm going to plug x plus h in for x. F of x plus h minus f of x all over h. The limit as h goes to 0. I did a little distribution there, minus that. Again, what do we have to do? We're going to have to multiply the top and bottom by the conjugates of this. So the square root of that plus the square root of this. Okay? Now, you could, if you didn't want to, if you just want to leave it as x plus h, because you're not going to let h be 0 eventually, you can just multiply by the conjugate right away. You can multiply it by root 4 times this plus 5 plus this root. You could have done that right away instead of distribute. That's fine. This and this is going to give me 4x plus 4h plus 5 minus this entire quantity. So the 4x's are going to cancel, and the 5's are going to cancel, and you're left with 4h up top. 4h up top over h times the conjugates. Bye-bye h's. Now I can let h be 0. So it's going to be root 4x plus 5 plus root 4x plus 5. So there's 2 of them. Again, if h is 0, that's not there anymore, so you have this plus this. 4 over 2 is 2. 2 divided by the square root of 4x plus 5. It's a little harder to catch a little trick that's going on. Again, when I come back, I'll ask, hey, does anybody see a trick? Does anybody see how the general power rule is going to work for derivatives? All right, anyway, folks, get on that homework. All right, let's get that done quick so we can check in a bunch so we feel confident. Let's get that homework set 3 and a homework set 4 done this week so we can focus on dominating that exam, that quiz and that exam. All right, the due dates are in Skyward. They are there, folks. That is it for this Wednesday video. This is Yak Math Videos signing out.